Welcome to my presentation, NorNet, a Linux and open source software-based international platform for networking research. My name is Thomas Drebold and I'm working for the Simula Metropolitan Center for Digital Engineering in Oslo in Norway. Well, let me first introduce you some motivation of our work before I come to some basic details about multi-homing and multipath transport. For I finally will present you the NorNet testbed, with particularly some interesting details about how we implemented the infrastructure regarding to virtual machines, containers and multi-home networking. Well, first let us look at the motivation. What was the idea of our work? Now, let us look at classic internet communication with the most basic example, web browsing. For web browsing you have a browser PC as well as a web server, and then you have to establish a connection to the web server over TCP and finally request the objects of the web page. In this case we have classic client-server communication. That is, you have one IPv4 address for the browser, one IPv4 address for the web server, and then you establish a TCP connection with three-way handshake. This is of course, as I've said, classic internet communication. It's the way the internet is working for around 40 years now. But of course nowadays we not only have this classic client-server communication, we have new things like Internet of Things, smart city, virtualization, sensor networks, mobile broadband and cloud computing and many others. So we have more strict requirements on the communication, and particularly nowadays we also have IPv6, the successor of IPv4. In fact, nowadays most devices are dual stack, that is being able to communicate with IPv4 and IPv6. So usually you have multiple IPv4 and IPv6 addresses per interface. And also nowadays quite common is mobility. So you have in your pocket quite obviously a smartphone which has at least Wi-Fi and 4G, 5G connectivity. So mobility is quite common thing. Also having multiple interfaces. Classically this was of course routers, but particularly your smartphone is also a device which has multiple interfaces. As I've said, Wi-Fi, 4G, 5G, 3G, Bluetooth, and same is of course also for your laptop, at least if you are not using an Apple device. So usually you have Ethernet as well as Wi-Fi at least in your laptop computer. So that is, you have multiple interfaces, multiple addresses. What can you do with this? Well, you have the possibility to do multi-homing. That is, you can configure a device to be connected to multiple networks simultaneously. In the simplest case, a network with IPv4 and another network with IPv6. And particularly, of course, you can use this for redundancy. You can connect your computer, for example, to 2 or even more internet service providers. So if one connection goes down, you have still other connection. So we do not lose connectivity. So redundancy is quite a nice thing, of course, if something goes wrong. So what's the problem with redundancy? Look at this internet news here. He does not look very satisfied about this redundancy. What's the problem? Well, if you have 2 internet connections, obviously from each of the internet service providers you receive a monthly bill. So redundancy is expensive. And of course this is not nice. So usually then you pay twice the amount for one internet connection just to have redundancy. In the usual case nothing goes wrong, you have both connections. So you pay more and do not have a benefit. Well, of course there could be a benefit if you use multipath transport. It is, if you have 2 internet connections, by not using them both simultaneously, to have at least higher download speed. This is nice, yes. So with TCP you cannot do this. TCP establishes a connection between two IP addresses. But with an extension, multipass TCP, you can. You get support for multi-homing as well as multipass transport. Or if you are using the Stream Control Transmission Protocol SCTP, you can use the extension concurrent multipass transfer for SCTP. So in both cases you get multipass transport. So it's an interesting topic in research and standardization, which requires more investigation. So let us look at some more details about multipass transport and the underlying multi-homing. For example, with MPTCP or CMT-SCTP. Well, how does it work? On the application layer of the OSI model, you have the application protocol, for example HTTP, HTTPS, or any other protocol you like. Then the protocol in the user space, of course, communicates with the kernel networking API or the socket API with the transport protocol implementation. That is MPTCP or CMT-SCTP capable TCP or SCTP implementation on the transport layer, and on the network layer, of course, you have IPv4 and IPv6, usually, as I've said, dual stack today. So in this case, of course, MPTCP or CMT-SCTP can then establish subflows over IPv4 or IPv6. You can even mix IPv4 and IPv6 subflows for the same MPTCP or CMT-SCTP connection. In the most extreme case, for example, you can start in a pure IPv4 network, later add IPv6 addresses, and later remove the IPv4 addresses, having an upgrade from IPv4 to IPv6 without breaking the transport connection. Of course, this is the most extreme case, but it's quite convenient that you can do this if you like. So now you have subflows, but you still need some decision about which subflow to use for a certain kind of segment of payload data. And this is the scheduler. So far so simple, but of course there are some challenges. The particularly challenge of multipass transport is fairness. So in the easiest case you think about subflows being disjoint in the network. But of course there may be shared bottlenecks. So if an MPTCP connection with multiple subflows shares the same shared bottleneck in the internet with a concurrent TCP flow, of course, if each subflow behaves like an independent TCP connection, it's quite unfair. Then you get n times the bandwidth of the concurrent TCP connection over the shared bottleneck. And fairness is not the only challenge of multipass transport. Also, of course, you have to think about scheduling, which subflow to use. So obviously, if you have a saturated flow, you should use all the subflows. But of course, in some other cases, you have maybe latency sensitive traffic, which is not saturated. Then of course, it may instead make more sense to use a path with a low round-trip time. And obviously in the internet, paths can be very dissimilar. That is, very dissimilar bandwidth, latencies, packet losses. So it's a challenge, and of course a topic of research and standardization work. Well, let us look how can you use MPTCP as an example. You can do the same, of course, with CMT-SCTP as well, but in this case I will just introduce you some more details about MPTCP. Well, MPTCP itself, the protocol, is already defined as an RFC, and it provides an extension to bring multi-homing and multipass transport to TCP. And particularly it's important to note that it's backwards compatible with TCP. This MPTCP instance can connect to another MPTCP or TCP instances. If the other side cannot talk MPTCP, it will just use plain TCP. So it's quite compatible, and particularly MPTCP traffic on the network looks like regular TCP traffic. That is, it will work over middle boxes like network address installation, port address installation, firewalls and so on. So it's quite compatible, which is quite a nice thing. And of course, if you want to use it for Linux, there is implementation from Université Catholique de Louvain-la-Neuve in Belgium, which is quite advanced. And also for FreeBSD there is a development version available from Swinburne University in Melbourne. Although this version seems to be not developed anymore. I'm not sure about the status, but at least the Linux version is of course under active development. So it's possible to use it, particularly of course with open source under Linux. Well, so obviously you need an MPTCP kernel, but does it work out of the box? Well, let us look at an example. We have a PC here, which is connected to the internet over Ethernet 0 to the first ISP and Ethernet 1 to the second ISP. Well, of course you have a default route over Ethernet 0 and a default route over Ethernet 1. Would MPTCP directly work out of the box here? Unfortunately not. Problem is, if you have the lowest metric, routing metric, over ISP 1, that is Ethernet 0, all the traffic will use Ethernet 0, so you do not get what you want. You have to do a little bit more. The solution under Linux is routing rules. I will explain this a little bit more in detail. In fact, with routing rules you create separate routing tables, one for each ISP, and then select the right routing table for an outgoing packet according to the source address of the packet. So let me show this as an example. We give the Ethernet interfaces now addresses 10.1.1.42 in a /24 network for Ethernet 0. We configure a default route, here in this case to 10.1.1.1. And now we want a separate routing table. Call this table number 1. So since this table number 1 is empty, we have to define a route with scope link first and then add a default route as above. So now we have, in addition to the main routing table, a table number 1. We can do the same with Ethernet 1 as well. In this case 172.16.142 as /24 network with a default route. And we put this information into table number 2, that is link scope, as well as default route. So now, in addition to the main routing table, we also have two other tables, table 1 and table 2, corresponding to ISP 1 and ISP 2. Well, and as I've said, we need a form of selector for the outgoing packets. So we add a rule: if the packet is coming from the address 10.1.1.42, we use table number 1. And if the address, source address of the packet is 172.16.1.42, we use table number 2. Far so good. I come to some more details on the next slide. Important to mention is we have now table number 1 and table number 2, but of course you can also give these tables symbolic names. For example, label them after the internet service providers, for example Optus and Telstra. So let us look what we have configured now. We have routing rules, particularly selecting table number 1 or table number 2 according to the source address of Ethernet 1 and Ethernet 0. And we have the possibility, of course, to do mapping, and particularly I mentioned there is a table named main, which is in fact table 254, which contains the normally used routing table. So if we have other addresses than the two addresses we have configured in the example, this main table will be used. So then we have table number 1 as I've said, with the default route and the link scope, and the same for table number 2 with the default route over the second ISP and again the link scope. So then if the packet does not come from one of these two addresses of the Ethernet interface, then there is the main table with the default route over the first ISP and the link scope for the two Ethernet interfaces. So far so good. So can we do the same with IPv6 as well? Of course we can. We can add an IPv6 address to Ethernet 0 and again define table number 1. IPv6 is of course a different network layer protocol, so it has its own routing tables obviously. So in this case of course we use the IPv6 table number 1 before we had the IPv4 table number 1. So of course they are different from each other. Well, this is the first ISP, then we can do the same with the second ISP in IPv6 table number 2, and again we define the IP routing rules for the IPv6 source addresses to use either table number 1 or table number 2 according to the source address used, source address of Ethernet 0 or source address of Ethernet 1. Well, now when we now use MPTCP or SCTP, then according to the source address for an outgoing packet, the right routing to a table is used. So now the machine can communicate over both interfaces, that is over both configured network internet service providers. And particularly then of course it can make use of all these addresses. So in total we have now 4 addresses, 2 IPv4 addresses, 2 IPv6 addresses. And all these source addresses can be used by our configuration now. This is what we want. So now MPTCP could in fact use all these addresses for establishing subflows. So how can you test this? Obviously you need an MPTCP capable kernel. You can get it from the Git repository, from the developers at Université Catholique de Louvain-la-Neuve. Compile it and boot it and enable it so that all connections are now MPTCP capable. And of course you can test the routing with ping, and particularly an interesting test tool is netperfmeter. I come to this test tool later again, which has the possibility to turn selectively MPTCP on and off, so we can make comparisons between TCP, SCTP, TCCP, UDP, and of course MPTCP. And particularly recommended may also be to use Wireshark to dissect the traffic, and of course Wireshark can also dissect the protocol data of MPTCP, so you can get all the details about observed flows in the network by using Wireshark. Well, so far so good. We have now multipath transport with MPTCP. Now I come to our testbed. Well, of course, as I've said, multipath transport is a topic of research work. So what I and my colleague wanted to do a couple of years ago, still working at the University of Essen in Germany, we wanted to do research on CMT SCTP as well as MPTCP. So obvious first step was to create a lab setup. So we asked the sysadmin to give us some old PCs, some old network cards, some old cables and a couple of switches. Put everything together and obviously it did not work. It was quite cheap setup, so the components were in fact almost for free. They were already there, but it was only cheap on the paper. And, some of these hardware components had quite strange effects. For example, network cards in combination with some of the switches suddenly changing bandwidth from 100 megabit per second to 10 megabit per second, and after a few milliseconds changing back to 100 megabit per second again, which of course triggered a lot of bugs in the SCTP implementation we used at this time in FreeBSD for CMT SCTP. So there was a lot of debugging work necessary before we finally made the setup working. But nice result, of course. Then after all the work of weeks and months of work, our simulations we made in advance were actually quite well met by the reality of the setup after all the debugging work, and we were able to provide a lot of bug fixes to the FreeBSD open source community. And as part of this, I wrote the mentioned software tool NetPerfMeter to compare protocol performance. So actually this setup led to a lot of new ideas and learning effects. And one of the ideas was, of course, well, we did research on internet protocols, but obviously this lab setup here is an intranet setup. Let's go to the internet. So we were then able to convince colleagues at two other universities, University of Applied Sciences at Burg Steinfurt and Hainan University in China, to create similar setups connected to, at each site, two different internet service providers. So we had a multi-homed setup with two ISPs at each site, at each of these three sites, two in Germany and one in China. So we were able to do intercontinental communication with multipath transport, with CMT SCTP as well as MPTCP. So quite interesting setup, and we did a lot of measurement work and analysis of performance and made some performance recommendations. So of course this led to a lot of new ideas, and one of the ideas was, of course, can we make this whole setup bigger? Of course this requires funding, but fortunately there was funding. Actually the Similar Research Laboratory in Norway had some idea of creating a multi-homed research testbed in the internet called NorNet. So they made a job opening, I applied, and a few weeks later I was moving from Germany to Oslo in Norway to start building the NorNet testbed. And NorNet consists of two parts. One is NorNet Core, which I today in this talk will introduce in a little bit more detail, which consists of landline connected internet setups at different sites, having deployment of a couple of servers at each site, hosting virtual machines for research experiment. And some time ago we had 21 locations, 11 in Norway and 10 abroad. But of course landline is not the only kind of network we have today. Also quite important is mobile networks. So NorNet has therefore also another part called NorNet Edge, for which we distributed around 200 embedded systems all over the country of Norway, running Debian Linux and connected to different mobile broadband providers here in Norway. I will not go into too much details about Edge here, because I want to show you a little bit more around NorNet Core. NorNet Core, as I mentioned, it has had 21 sites some time ago, 11 in Norway and 10 abroad. In the past, number of sites abroad has a bit decreased, so hopefully in the future we can find some more new hosts in other countries again to extend the network. But we still have 11 sites in Norway, and these sites are connected to up to 4 different internet service providers with quite different access technologies. For example, fiber connections for research network, business grade fibers, consumer grade fibers, and ADSL connections. And also where we have IPv6, of course, we also provide IPv6 support. So quite interesting, and particularly then of course with such a setup you get a very interesting routing between the sites. This is a view made by our tool HyperContracer, which is also now included in Debian Linux. This shows connections between the sites according to the autonomous system numbers. So you see, particularly between Europe and East Asia, there is of course a lot of diversity in the connections. For example, connections can go over United States westwards or eastwards via Russia or Dubai. So quite interesting, and particularly this changes over time. This observation is over 1 month in 2016. So quite interesting, but I cannot go into too much details here because I want to show you a few interesting implementation details. Well, we have of course a lot of remote servers, and when we say remote servers, well, our servers are really remote. We have a site in the city of Longyearbyen on the island of Spitsbergen, which is in the far north of Norway at 78.2 degrees north. From there it's around 1,200 kilometers to the North Pole. So we deployed our server setup there on a nice spring day in April. It's a nice sunny weather at minus 30 degrees. So you can imagine how it looks there when the weather is not so nice and sunny. But cold temperatures are not the only challenge for such a setup. On Spitsbergen there are wild ice bears. They are roaming around the area. So it's actually quite dangerous to go outside of the city of Longyearbyen. And this is the road to Longyearbyen. So obviously you have to drive a snowmobile. So no cars. And of course, as I've said, there is the danger of wild ice bears. So obviously, you can imagine if something with the site goes wrong and some repairs necessary, it's maybe a challenge to actually go to the site and do some repair. So what can we do about this? Particularly because we have experimental software. And there is Murphy's Law saying that anything that can go wrong will go wrong. So we have a lot of research software running, which is by its nature experimental. So if something goes wrong, how can we avoid that it makes our site setup unusable, so that somebody has to go to the site and do some manual repair work? Well, the idea was quite simple. We started with a quite basic setup of Ubuntu Linux LTS. Currently we are running 18.04. We started with 12.04 and soon we will upgrade everything to 20 or 22.04 LTS. So with this lightweight setup we run KVM, kernel-based virtual machines, and everything experimental goes into virtual machines. That is particularly the router software doing all the routing with the IP rules, which goes into a virtual machine running on a dedicated server, and all other servers host virtual machines with research node software. I'll come to this later, and possibly other custom virtual machines for research experiments. So if something goes wrong, we can just log into the host machine and for example repair the virtual machine or copy a complete new virtual machine. So avoiding that too much work is necessary at the site itself. Well, how does the physical machine setup look like? As I've said, we have chosen Ubuntu Server LTS due to its 5 years long-term support, and we made a bit of customization. And one customization was initially we started using RiserFS. RiserFS, some people probably mean that it has some bad image because it's named after the author who finally killed his ex-wife. But actually, RiserFS never killed our data. So it has been shown to be really robust, and particularly not needing manual file system checks, which can be quite annoying at remote machines, which then fail to boot and need some manual work directly at the machine. But this was avoided by using RiserFS. So it was a bit unfortunate that it was finally removed from the Ubuntu installer. At the beginning of our NorNet project, BTRFS was already there, but of course it was not in a really stable state, missing, for example, the possibility to do a file system check and such. Well, so therefore RiserFS, which showed quite good performance and was quite reliable. Nowadays, unfortunately, for new installations, we have then to use BTRFS, which is nowadays also reasonably stable. So X4 was never a really good option because of its need for manual file system checks in case, for example, sometimes the machine was turned off unattendedly, for example, by unplugging it. Yeah, well, on top of the lightweight installation of Ubuntu Server LTS, we run everything in kernel-based virtual machines. Originally, at the very beginning of our project, we used VirtualBox, but this has proven to not be very stable, and particularly for VNC, it required the installation of a blob package of Oracle to add this VNC support, and it showed to be not that stable, so we wanted to avoid this blob altogether and finally choose KVM as the replacement, which has proven to be quite stable. Well, this is the research node software. Come to some details later, but first let me introduce the routing. As I've mentioned before and introduced with the routing rules, of course, it's necessary to do an establishment of all these routing rules and different routing tables, one for each ISP and one for each IP protocol version. Of course, we wanted to give the researcher the possibility to do his own research with an own IP address for each ISP at a site. Obviously, when we would ask a site host for our own /24 public IP address range for IPv4, no chance, of course. Nowadays, the IPv4 address space is exhausted, so no chance to get a reasonable number of IPv4 addresses, one for each research experiment. So the idea was therefore, well, we want, of course, to expose the user to all the effects of the current internet, like delay, latency, jitter, bandwidth, and such. So therefore we do tunneling. We have for our router only one public IPv4 and one public IPv6 address per site per ISP, and we establish an internal tunneling where we can configure our own internal address range. And of course, since we use our own address range, this can be done quite systematic for IPv4. It is 10.provider_id.site_id.node_id s/24 per site. And the same for IPv6 with our own IPv6/48 prefix, giving each site its own /64 network. And another requirement for the another need for the tunnels was, of course, the communication with the external internet. Of course, with this scheme you can directly communicate with all other sites of the infrastructure, but if you go outside of the NorNet core network range, of course you go to the internet. And particularly we have, for example, sites in Germany which have very strange laws regarding copyright and file sharing and such. And therefore Also this is the issue in Germany. You hardly find free Wi-Fi networks because of these liability regulations in Germany. So in fact, if you ask somebody to host a site like NorNet Core, you will ask who is liable if some user, for example, tries to download some video or something like this. And then it's very complicated because it can be very expensive. So the idea is if there is external communication necessary with the internet, for example for downloading installation packages, in fact all the communication is tunneled to the Simula side, going into the internet with a Simula IP address in Norway. And of course, since the Norwegian regulations apply, this is much more relaxed than, for example, in Germany. So this is the tunnel box, and particularly we have now our nice addressing scheme, but IP addresses are difficult to remember, so therefore it was then quite easy to also add own DNS setup using bind with our private top-level domain .NorNet. So we can also name all our machines, particularly also provide a reverse lookup of the names. So for example, we have a machine storn.quantel.simula.nornet. So this is the site simula.nornet using the ISP Quantel and the machine storn. And particularly, of course, since Norwegian names can also have special characters, of course, this setup also supports Punicode. The same also for our Chinese site. So it's quite convenient, and particularly with DNS, we can also directly put the SSH fingerprints into DNS as well as geolocation information. And in addition to this, we also install a squid proxy on the router, because if we want, for example, have package updates, instead of letting each research node, as each virtual machine, download everything over the infrastructure from Simula and the internet, we just let squid proxy do some caching on the tunnel box router itself. That is the router. And now I come to the research node. The research node is in fact based on the PlanetNet Central software, PLC software, which is based on Fedora Core. At the moment we still are using Fedora Core 25, which is of course a bit out of date now, so it would need an update. We're currently thinking about upgrading this software. And we have equipped the research node, of course, with a kernel running MPTCP in version 0.94. And what a researcher then gets is in fact a container, LXC container, a so-called sliver. It is the container runs an own installation of Fedora Core 25, and the researcher has the possibility to install custom tools just with the normal onboard mechanisms of Fedora, that is DNF. And particularly, as I mentioned, each research experiment, that is each container, gets its own IPv4 address as well as its own IPv6 address for each ISP of the site. It is the researcher can use this IP address undisturbedly. Of course, IP addresses from our internal NorNet range. And with this, the researcher can then install his own software that is using DNF, or of course even build it on the machine itself, or just copy it. The researcher has sudo permissions. Nice thing to mention about this PLC software is also that it makes extensive use of BTRFS clones to just avoid duplicating the whole installation for each research experiment. That's in fact the installation of a research experiment container is very lightweight. So it's in fact just a clone of a BTRFS snapshot, with some customizations per research experiment. This is the usual way research experiments are run in NorNet Core. Of course, there is also the possibility to instantiate custom virtual machines, which currently requires some manual setup, but of course if a researcher needs, for example, a FreeBSD machine or a very up-to-date or customized Ubuntu machine, this can be made possible as well. But usually there is, as I've said, the research node software based on Planet Lab Central, and so the physical server setup for research experiments looks like that there are KVM-based virtual machines running this PLC-based node software inside the KVM, and for each research experiment at this node there is then an LXC container, so-called sliver, instantiated, which is in fact just using BTRFS cloned snapshot of the base Fedora Core 25 image. And of course we can run multiple research nodes on the physical machine, as well as custom virtual machines for example, special operating systems. And if you look into such a research node, well, obviously it looks like a normal Fedora core system, providing you an Ethernet interface with all the addresses of the site. In this case, this is the look of a machine at Hainan University, which has two ISPs. One is Cernet and the other one is China Unicom. So the machine has two IPv4 addresses and two IPv6 addresses. And for some convenience, we have also added a tool called System Info, which on login presents you all the information about the IP addresses as well as the SSH key fingerprints. And as I mentioned in our DNS, in our internal DNS, also these SSH key fingerprints are stored, so you can directly securely log in with SSH, just letting SSH check the fingerprints. Well, this is the research software, so I come to the conclusion of my talk today. I'm almost over with the 45 minutes. Well, we have created our NorNet testbed for research on multi-home systems, multi-bus transport, but also other topics like redundancy and resilience. And particularly to mention is NorNet Core is an open testbed, so if you are interested in research within NorNet Core, just ask and we can make it possible to let you use our infrastructure. And of course we are currently thinking about extending NorNet Core's scope beyond the multi-pass transport topic, particularly around, for example, internet routing and ideas to do some measurements in the internet where multi-homing is of interest. So there is currently work on extending NorNet Core, particularly by obtaining funding, of course, around network function virtualization and software-defined networking, as well as the usage for cloud computing and applications. Particularly, you can see all the NorNet Core infrastructure as a private multi-cloud. So quite interesting things to do. And if you are interested in more details, have a look at our NorNet website for further information. And particularly, we are very committed to open source software. So a lot of open source software has been developed out of NorNet Core. So have a look at our various websites and of course GitHub and Bitbucket repositories. And of course we have a lot of research literature as well, which you can find on our publications page. So now I have to thank you for your attention, and at the conference hopefully you can ask questions as well. Otherwise you just can write me an email. Thanks for your attention. Have a nice day.